probability. We're going to start off with a quick review of the lecture notes, and then we're going to jump into the stuff listed at the end of the lecture notes, the video content. Remember to like and subscribe to the Agora Math Circle YouTube channel, and remember to watch all the way through and make sure you understand all the examples, because 3 of the examples presented in this video will be on your classwork. Let's begin. We're going to start off by looking at a data set. Here's a set of 13 data points. They're just numbers between 1 and 9. Now, the first thing you always want to do whenever you're analyzing any data set for any reason is put the data points in order. This data set has a simple mode. The data point that occurs the most often is the mode. There's 1, 1, 1, 2, 1, 3, 3 4s, 2 5s, 1 6, 1 7, 1 8, and 2 9s. The most we have of any number is 4. So 4 is our mode. But what if, say, we didn't have this second 4 here? Then 4, 5, and 9 would be our modes. But if everything is tied, then there's no mode. You'll notice that it was way easier to find the mode once we had the stuff in order, because you can see the groups of numbers. You can see that there's 3 4s. And that's one of the main reasons that we put them in order. But another reason we put them in order is so we can find the range. And the range is the difference between the highest and lowest values. Our highest value is 9 and our lowest is 1. 9 minus 1 is 8, so our range is 8. So let me keep track of the step down here. Our mode is 4 and our range is 8. All of this can be found in your lecture notes. The next thing we can find is our median. Now, the median is the number in the exact middle of the set. You'll notice I started on each side and numbered the ones on the edge 1, then 2, then 3, then 4, then 5, then 6, then finally the middle. When the 2 numbers meet, that's the middle, right? You can do it by crossing out the ones on the edge, but again, this only works when they're in order, so be sure to order them first. Now, arises an issue. What if we were looking for the median, but we have an even number, right? So say we got rid of one of these, we got rid of that last 9, then 4 and 5 would be tied for the middle. So what you do is you average these 2 numbers, 4 and 5, and you get that the median would be 4.5. However, when we're looking at the median, we also round to the same number of significant digits as our data set has. So since our data set only has 1 significant digit, then what we round to also has to have 1 significant digit. So since 4.5 rounds to 5, our median would still be 5. So the next thing we want to do is find the arithmetic mean. That's a big word. You might know this as the average, where we just add everything up and divide by the number that there is. In this case, our average is going to be 5.2. I'm not going to sit here and add up numbers and then divide by 13, but the average is 5.2. But what's more significant is that while average colloquially might mean arithmetic mean, in our case, average can refer to any measure of central tendency. Even the median could be considered the average. The average, when talking about data, refers to the center of the data set. So, any of these measures of centers, not range, range is not a measure of center, mode, median, arithmetic mean, can all be considered averages. So we could say the average is 5.2, we could also say the average is 5, we could also say the average is 4. Lots of times in reports, when they say the average, they mean the median. That's really commonly used as the average. Now the difference is that these are measures of central tendency of the data. That means, where do the most data points lie? What is, if we take the aggregate of all the data points, what do we get? Range is a measure of distribution. It's from this center, how far is everything spread out? So we have a measure of distribution and 3 measures of central tendency. Any measure of central tendency can be considered the average. So next we're going to move on to another measure of central tendency, another average, the geometric mean. The geometric mean is usually not calculated by hand when you have this many data points. So let's look at something a little easier. The geometric mean between 25 and 36. Now, The way to find the geometric mean between two numbers, or n numbers, so we have n numbers where n equals 2, we have 25 and 36. We want to find the geometric mean. What we do is we multiply them all together. I'm just going to write out the prime factorization. And then we do the nth root of that. So that would just be the square root, so we don't actually need this 2. The square root of 5 squared times 6 squared is 5 times 6 equals 30. So the geometric mean between these two would be 30. Now, with 13 numbers, that would mean you have to multiply them all together and then take the 13th root. You won't be asked to do that for this many numbers without a calculator, don't worry. But in this case, the geometric mean, if you put it into a calculator, is 4.4. The last thing we're going to be discussing is the frequency and how to display it. Now, the frequency is, again, really useful to have things in order. So the first element is 1. The frequency of 1 is 1, because there's only one 1. Then 2, the frequency of 2 is also 1, 3 is also 1. The frequency of 4 is 3, 5 is 2, 6 is 1, 7 is 1, 8 is 1, and 9 is 2. Oops. Now, we display these in something called a histogram. On your lecture notes, you can see a way better picture of this than I've drawn here, but this is a histogram. On the x-axis, you put down the element, and you don't skip any. Say there had been no 6 in here. Say we got rid of the 6. Now, we wouldn't get rid of the 6 here. We would keep this here and put it at a frequency of 0. So you don't skip any elements even when they're in the middle. You have to have things evenly spaced. But then you just use the y-axis to denote the frequency of the element. So 1, the bar here would come up to 1 because the frequency is 1. You can see 4 comes up to 3, 5 comes up to 2, 6, well, since we got rid of the 6, it's at 0, and you write the frequency on top of each bar. It's basically like a bar graph. You did those probably in 4th grade. Histograms are super simple, super easy. You'll be fine. If you'll turn to the beginning of your lecture notes, on the first page, we have this example problem. We have a student has an average score of 80 on her first 4 tests. What must she score on her 5th test to raise her test average to an 82? Assume average test scores are calculated with an arithmetic mean. All right, so what do we have here? We have the average current score, which is 80, and we're going to call that x. Then we have the average score that she wants, which is, whoops, I wrote that down wrong, which is 82. Now, what does that mean? Well, that means that her current test score total, if we added up the scores from all of her tests, we would get, since there's 4 of them, 4 times x equals 320. She wants a test score of 82, and that's going to be including 5 exams. So we want 5 times y equals 5 times 82 equals 410. So how do we figure out what she has to get? Well, her current test score total is 320, and she wants to raise her total to 410. To do that, we just subtract 320 from 410, and we get that she has to earn a 90 on her exam. All right, let's take a look at a geometric mean problem. 2 numbers, x and y, have an average arithmetic mean of 6, which means x plus y is going to equal 12, right? Now, the geometric mean is 2 rad 5, which means that x times y is going to equal 2 rad 5 squared, which is 20. We can find x in terms of y, and that means that x is equal to 12 minus y. We substitute that in, we get a quadratic, and we solve the quadratic that you all know how to do from session 7. We get y equals 2 or 10. And those are the 2 numbers, 2 and 10. Let's verify that. Their arithmetic mean, their average, okay, 2 plus 10 is 12, divided by 2 is 6. Check. And we have, all right, 2 times 10 is 20. The square root of 20 is 2 rad 5. Check. And so our answers are 2 and 10. Final part of the lecture notes is looking at probability. As you probably all know from last year in math circle or from in school, probability is just the fraction of cases that we want that satisfy our condition over the total number of cases. So if it's how many ways can we, or what's the probability when we roll a dice it comes up even? Well, 3 of the numbers are even, there are 6 total numbers, so the probability is 3 in 6, or 1/2. And that's all there is to probability. So let's take a look at the practice problem on the lecture notes. You can read through the example problem first and try the practice problem. I'm going to give you the solution to the practice problem on there in 3, 2, 1. So the question is, if two people both pick a different number between 1 and 10, 1 and 10 are included, then what's the probability that they pick an odd one and an even one? Let's first take a look at a theoretical approach. The first person can pick an odd or an even, and the second person can pick an odd or an even. In this slot we get 2 odds, in this slot we get an odd and an even, in this slot we get an odd and an even, and in this one we get 2 evens. Since half the cases, 2 out of 4 of these cases, you get odd and even, we would expect that the answer is a half. But let's do it mathematically as well. For the top, we want to figure out how many ways we can satisfy our condition. Well, there's 5 ways to pick an odd number and 5 ways to pick an even number, so there's 25 odd-even combinations. But we got to figure out the total number of ways, and the total number of ways is going to be 10 choose 2. How many ways can we pick 2 things from a group of 10? We learned this last session. So we get 25 over 45, which is 4 in 9. But these aren't the same. So what went wrong? If Joe picked, say, 5, Jack can't pick 5. So he has a greater chance of picking an even number since one of the odd ones is already taken. So the 2 even, this even one here, they're going to lose 5 scenarios, right? Because they can't both pick 2, they can't both pick 4, they can't both pick 6, etc. And they're also going to lose some here too. And that is what, oh my god, I'm sorry, this should be a 5. And that is what pulls the answer above 1/2, because these ones have to go down. So these boxes are going to be a little bit smaller because they can't choose the same number. And that's why our answer is slightly over 1/2. The next thing that we're going to do is take a look at how we can multiply 2 probabilities together. Now, first let's take a look at when we roll 2 dice, what's the probability we roll a 12? Well, using what we already know about probability, we know that there's one case in which we roll a 12, when we roll 2 6s. We know that there's also, since there's 6 possibilities in each dice, we know that there's 36 possibilities in total for rolling 2 dice. So we know that the probability is 1 in 36. However, there's another way to do it. Now, this other way isn't actually simpler in this case, but in many other problems, using this other method, it's going to be a lot quicker than counting out every single case individually. We use this formula. When we want to find the probability of 2 events happening, probability of A and B happening, then we take the probability of A and B happening equals the probability of A happening times the probability of B happening. So what are our A's and our B's? Well, our A is that the first dice lands on 6, and our B is that our second dice lands on 6. Probability of both of these is the probability of each one happening multiplied together. The probability that the first dice rolls a 6 is 1/6, and the probability that the second dice rolls a 6 is also 1/6. Now, this means that we have to just multiply 1/6 times 1/6 equals 1/36. And you'll notice, since we got the same answer, that you could have used either of these to solve the problem. But again, sometimes if you say have, I don't know, what's the probability of rolling an 18 with 3 die, you might not want to have to count out how many possibilities there are. This is usually the toughest thing to do. Count out the total number of possibilities. That's going to be a lot of multiplying. And then you also have to go back and find all the cases, which is also a lot of work. And the easiest thing to do would just be to find the individual things and then multiply them together. There are some major limitations on when we can use this formula. Now, when we roll the first dice, that's not going to change at all the probability for what we roll on the second dice. Now, what that means is those two events are uncorrelated. The outcome of one is not going to change the outcome of the other, right? If we roll a 6, that doesn't make it less likely for us to roll a 6 the next time. You should know that these are independent events. They do not matter what happened the last time, okay? So we call them uncorrelated. And uncorrelated events, we can totally use this formula. However, in correlated events, we can't. So let's take a look at an example, and we'll see that we get the wrong answer when we use this formula. The problem we're faced with here is to find the probability of, if we draw 2 cards from a deck, drawing a diamond and then a heart. But the issue here is that if we multiply, we would think that there's a 1 in 4 chance of drawing a diamond, right? And a 1 in 4 chance of drawing a heart. So if we use the formula, 1 in 4 times 1 in 4, we get that the chances are 1 in 16. However, this is entirely false. The chances are not 1 in 16. And let's go over why. And then we're going to go over how we can modify our formula to compensate for this. So here I have a deck of 52 cards, right? Now for the first card I draw, 13 of the cards in this deck, 13 out of 52 cards are going to be diamonds. Now, suppose I draw a diamond. Now, I have to figure out the probability of drawing a heart. Well, there are still 13 hearts left in this deck, but there aren't 52 cards in here anymore. There's only 51 because I've removed a card. So, if I were to draw again and get a heart, that would be 13 and 51. Now, multiplying these two together, we get that the answer is 13 in 204, which is definitely not 1 in 16. So how can we modify our formula to compensate for this? The way we compensate for this is, instead of saying the probability of A and B is probability of A times probability of B, we change it to probability of A times probability of B given A. Now, if the events are uncorrelated, then the probability of B given A is just the probability of B happening. But if the events are correlated, we'll notice that the probability of B is drawing a heart and A is drawing a diamond. The probability of B, right, drawing a heart, is 1 in 4. But the probability of B given A, the probability of drawing a heart after we've drawn a diamond, is 13 and 51, which is not 1/4. So, when we're using this formula, if we're going to multiply it, we have to use the probability of B given A as the formula instead of just probability of B times probability of A. Right? We'll notice that this gives us an entirely different answer than our original formula. So if you're ever doing a problem, you must use this formula if they're correlated events. If they're uncorrelated, you can just use probability of A times probability of B. However, you're technically using this formula because probability of B given A is just B when they're uncorrelated, but either way, try to use this formula. If you're ever uncertain of whether they're correlated, use this formula. This works for everything. The other formula only works when two events are uncorrelated. The thing about the problem we just did is that order matters in that problem, right? We want to pick a diamond and then a heart, but if we pick a heart first, then that doesn't satisfy the conditions. What if we had a problem like, what's the probability of the first 2 cards we pick being a diamond and a heart? Well, the formula that we use assumes that you care about the order. So let's talk about how you can figure out the same sort of problem, but without having to care about order. So imagine we have 9 cups and we're going to randomly pick 2 of them. Now we want to find the probability that one's red and one's blue. Logically, the probability that we'll pick a red cup and a blue cup will be equal to the probability that we pick a red then a blue plus the probability that we pick a blue then a red. So let's calculate those 2 probabilities and then add them together. So the work, if we use this method, looks something like this. First, we find the probability of drawing a red then a blue. The probability of just drawing a red is 6 and 9, and the probability of drawing a blue, given we've already drawn a red, is 3 and 8. This multiplies to be 1/4. Next, we have probability of drawing a blue, which is 3 and 9, or 1/3. times the probability of drawing a red, given we've already drawn a blue, which is 6 and 8, or 3/4. This also multiplies to be 1/4. We add the two together and get 1/2. But this was quite a bit of work. So there's actually an easier way we can do this. Now, using this formula, the probability of A and B equals probability of A times probability of B given A is useful. However, it's not always the best way to solve a problem. See, here we have using this, but if the problem isn't designating an order, then we usually don't want to use this, because if there's more than two things or maybe more than two events that are occurring, you'd have to go through, well, if there were 3 events that are occurring, you have to go through 6 of these just to get the probability. So sometimes this is not the way to go. And so we're going to go over an easier way to do this problem without having to do out each possibility, just using one fraction. We know from our probability formula that the probability of doing this is going to be the cases satisfied, the number of cases in which we can do this, over the total number of cases. So let's start by trying to find these two things. Now this is the work if we do it the other way. It already just looks way less. We just have to remember that traditional probability dictates that the cases satisfied over the total cases is the probability as long as each case is equally likely. Now, how many cases are satisfied? Well, that's how many ways can we pick a red and a blue? Well, that's obviously 6 times 3 equals 18 ways to pick a red and a blue. Over how many ways there are to pick 2 cups in general. There's 9 cups. We want to pick 2, so 9 choose 2 equals 36. 18 over 36 is 1/2. That's the far easier way of doing it. Now, the purpose of this problem is to show you that just because you have a formula doesn't mean you should use it. And if you're using a formula and it's going against what you think is common sense, and it's going against something you think is common sense, then you should just relook at how you applied that formula, see if you made a computational error, because more often than not, your common sense is going to be right about these sorts of things. So just remember that you can always solve a problem without formulas. You never need formulas to solve a problem. You only need your common sense. Formulas should just be used to speed up work. But if they're not going to do that, then you shouldn't use them at all. Last time we took a look at casework. Casework is in like counting the number of cases, right? In the last session where we learned to count. Now, casework can also be applied when we're looking at probability. So let's take a look at one problem that is going to require a bit of casework. If we roll 2 dice, what's the probability that we're going to roll a 6? It's important to note that all of our answers are going to take the form of 2 numbers being rolled, right? Okay, so let's make this column dice A and this column dice B. Each of these is going to be a way that we could roll them. So, say we rolled a 1 on dice A. We'd have to roll a 5 on dice B. If we rolled a 2, we'd have to roll a 4. If we rolled a 3, we'd have to roll another 3. If we rolled a 4, we'd have to roll a 2. And if we rolled a 5, we'd have to roll a 1. Now, if we rolled a 6 for dice A, there's no way we could roll a 6 in general because there's no 0 on this dice. And simply by making a table listing out the cases, we found that there are 5 ways for us to roll a 6. And that's pretty good. That's all there is to casework, right? Casework doesn't have to be incredibly complicated. The only thing that makes casework different than, say, a pure probability problem is that instead of doing everything algebraically, trying to figure it all out algebraically, sometimes it's just easier to list things out. Sometimes it's just easier to use your brain and make a list instead of trying to figure out mathematically the number of ways that there are. Problem solving means that you need to use multiple different strategies, and if your strategy is always to just do pure math, it's going to take you too long and be too difficult sometimes. Sometimes you just have to make a list to get 5 over 36. That was way easier than what it would have taken if we had taken a pure math approach to this. Let's take a look at an advanced casework example from the AMC 10. Now, this is the probability of having 2 dice and rolling a 7. But there's a catch. Instead of the probability of rolling a 1 being 1 out of 6 and 2 being 1 in 6, the probabilities are different. Instead of the ratio of probabilities of getting each number being 1 to 1 to 1 to 1 to 1 to 1, they're 1 to 2 to 3 to 4 to 5 to 6 respectively. Thus, we have to figure out first the probability of rolling each number on one of these weird dice. As it turns out, 1 is 1 in 21. How do we know this? Well, the total number of things here is 21. And 1 has 1 of them. So we can conclude that this weird hypothetical die has 21 sides. One of them has a 1, 2 of the sides have a 2, 3 of the sides have a 3, etc. From that, we find that the probability of rolling a 1 is 1 in 21, a 2 is 2 in 21, a 3 is 1 in 7, a 4 is 4 in 21, a 5 is 5 in 21, and a 6 is 2 in 7. All right, then we make the same table we did last time. A and B, we have 1 and 6, 2 and 5, 3 and 4, 4 and 3, 5 and 2, and 6 and 1. Now, each of these can be written out, right? So we have 1 and 6, well that's 1 21st times 2 and 7, right? Because we're multiplying these two together. The reason we can do that is because, again, the 2 dice rolls are totally uncorrelated. So we just multiply the 2 probabilities together. Now, as it turns out, the probability, we're going to add up all these probabilities, right? But as it turns out, through here, we have a 1 and a 6 and a 6 and a 1. They're going to have the same probability. So instead of adding them both in, we could just find this and multiply it by 2. The same with the 2 and the 5 and the 5 and the 2. The same with the 3 and the 4 and the 4 and the 3. So basically, what we're going to do is we're going to cut it in half, right here. And we're going to only look at this, but then we're going to multiply the entire thing by 2, right? Because this is just identical to this. The probabilities are the same. So then we come and we get 2 times each of these things. Now, we have like a 2 and 7 and a 1 and 7 here, and while that might make the fraction simpler, the better thing to do is to try to get a common denominator. So right here we have what they all are over 21 squared. We have 6 and 21 squared, we have 10 and 21 squared, and we have 12 and 21 squared, all multiplied by 2. Eventually, we get that it's 28 over 21 squared, all multiplied by 2. Now, 21 squared and 28 both have a factor of 7, so we take the factor of 7 out of the top, making it 4, and out of the bottom, making it 21 times 3. So we have 2 times 4 over 21 times 3. 2 times 4 is 8, and 21 times 3 is 63. So our answer is that the probability of rolling a 7 is 8 in 63, which is just a little over 1/8. That was really complicated. So essentially, casework is just, we're going to find all the individual probabilities and add them up. And really, that's what we did here. The most difficult thing in this entire problem was realizing what the probability of rolling each of these would be. That was the most difficult part of the problem. And that wasn't even that difficult. So what makes this problem so difficult? Each of the pieces of this problem are really easy, right? Factoring out of 7, adding up fractions, giving them a common denominator, multiplying 2 probabilities together. Those are all really easy. The hardest thing was figuring out what this expression really meant, the 1 to 2 to 3 to 4 to 5 to 6, how to convert that into a probability. As we figured out 2 problems ago, the probability of rolling a 6 is 5 in 36. So how do we convert this into odds? Well, basically, we say the odds, when we're talking about odds, we say the odds are, then we state the expression what to, this is the colon, it's read by 2, what to what, against X happening. So we usually say against, and that's what usually trips most people up. We're trying to figure out the odds against something happening because that's just how we use them in daily life. We say the odds against you winning are 5 to 1. The odds are 5 to 1 against you winning. The odds are 6 to 3 against, 6 to 4 against that person flipping this number or whatever. So let's try to figure out what the odds are against rolling a 6. Well, the first space is the number of cases, right? The number of cases that you will not succeed in. So since there's 36 total cases and we succeed in 5 of them, then that means 31 cases we don't succeed in. And then the second number is the number of cases that we do succeed in. So 31 to 5. And that's it. Now, that's how we go from a probability to odds, right? The odds are 31 to 5 against you rolling a 6. A quick example of the sort of problem you might see. If we have a 7% chance of X happening, what are the odds against X happening? The first thing we want to do is find the probability, which is pretty easy, 7 over 100. Next, the odds are 93 to 7 against, right? Because 93 out of 100 times X does not occur, and 7 out of 100 times X does occur. Last thing we're going to do today is talk about expected value. Now, we're going to explore this problem. You're entering a raffle. There are 20 tickets in the raffle for sale. They're going to pull the tickets. One person's going to win $100. One person's going to win $20. 4 people are going to win $5. And 14 people are going to get nothing. Now, it costs $5 to play in the raffle. So if you do this, you're going to lose $5. If you win one of the 4 $5 tickets, they're going to break even. And only if you get a $20 or a $100 ticket are you going to make money. And the question is, should you enter this raffle? Is it advantageous to enter this raffle? So, let's dive into how we figure this out. Now, first things first, we want to find the probability that each of these happens. Okay, so I'm going to add a probability section. Now, the probability that you win $0 is going to be 7 in 10. $4 is going to be 2 in 10. And then each of these is going to be 1 in 20. Now, in order to find the expected value, you take the value of each, you multiply it by the probability, and then you get the expected value of each, and then you add it all up. And that's the expected value. So $0 times 7 out of 10, well, big shocker, it's 0. $5 times 2 in 10, well, that's going to be $1. Now, $20 times 1 in 20, that's also going to be $1. But $100 times 1 in 20 is going to be $5. So the expected value from this is $7. So even though you only make money 1 in 10 times, you should play in this raffle because if the expected value is more than what you're going to pay. Let's try to verify the answer. Imagine if you bought all 20 of the tickets. How much is doing that going to cost you? It's going to cost you 20 times 5 equals $100 to buy all the tickets. But you'll win $140 by doing that. So if you bought all the tickets, you're going to get more than what you spent. That means that running this raffle, if you're the one running this raffle, you shouldn't be running it because you're going to lose money. So if buying all the tickets is going to make you money, then the expected value is going to be greater than the cost. And that means that you should play the raffle. It's statistically advantageous to play the raffle. That's everything you need to learn today. Just remember that you should go back through and make sure that you know everything and all the example problems in there, because just like last time, 3 of the classwork problems were included in this video. So if you go through this video and you make sure you understand all of the examples in it, you will be guaranteed to get at least 3 classwork problems correct. Good luck learning the content, and be sure to come on Saturday.
Don't forget to subscribe and like. If you have any questions, you can email info@agoramathcircle.org or comment below and we'll reply back. Maybe. And if you want to see practice things or anything about us, you can visit our website, which is basically the end of the email but without the info and the end. So bye!